So we're going to go over something known as Russell's paradox, which has to do with trying to construct a set that contains all other sets. So recall the axiom of regularity. Any set A must contain an element which is disjoint from the original set. Remember in Zermelo-Fraenkel theory, elements of universe, all sets. Okay, the only thing we can talk about are sets. Even the elements of sets are also sets. So why is the axiom of regularity included? So consider trying to construct the following set. S is a set. What elements are in it? All possible sets. So any set you can construct is an element of S. So it's a set that contains all sets. By the axiom of specification, once you have a set, you can make a subset, which is all elements on which a certain predicate statement is true. And the statement we're going to use is sets that are not elements of themselves. So if a set is not an element of itself, it goes into our subset. If a set is an element of itself, it goes into our subset. It does not, sorry. So our truth set, which we'll call B, okay, it's just the truth set of this predicate, is the set of all sets which do not contain themselves as elements. Okay, verbally it's awfully weird to talk through, but we've assumed that this is a set. The elements are any other set you can want. Okay. Then we ask, let's make a set where this statement is true. A set is not an element of itself. So the truth set of that is a set containing all sets that are not elements of themselves. So we started off by assuming S was a set. The axiom of specification says, make any predicate you want, and you can talk about the truth set. So the predicate that we're constructing is A is not an element of itself. So the truth set is, within the set of all possible sets, look for anything that doesn't contain itself as an element and construct this. Okay. This all started by assuming that S was a set. We're going to end up generating a contradiction known as Russell's paradox, named after the logician Bertrand Russell. So we assumed that we could start with the set of all sets. We derived there is a subset containing all sets that do not have themselves as elements. So does this subset B contain itself as an element? Since B is an element of S, remember S is all possible sets. Since B is a set, it must be an element of S. It might belong to the truth set, so it's possible to ask, is it an element of itself? Okay. But what makes a set belong to B is when this statement is true. Remember, B was the truth set of this statement, not an element of itself. So if this predicate is true, then B is not an element of itself, and therefore B is not an element of itself, so it belongs to the truth set of P. But the truth set of P was exactly the set B. In other words, assuming B is not an element of itself, we derive that B is an element of itself. But if B is an element of itself, then this predicate statement is false, which means that we're not in the set B. So this statement can't be false, can't be true. Okay? If P of B was true, we end up in a contradictory circle. So P of B can't be true, therefore it must be false. But if P of B is false, it's not the case that B is not an element of itself, so it is an element of itself. In which case, B does belong to the truth set of the predicate, and therefore it's true. So P of B is either true or false. Either way, we get a contradiction. So it can't be true and it can't be false, but it has to be one or the other, and the logical system is no longer sound. What caused this mess? Assuming that S existed. So the assumption that S exists must be invalid. There is no such thing as the set of all sets. Which brings us back to the axiom of regularity. The fundamental issue is that we had the possibility of sets being elements of themselves, and we were able to then use the axiom of specification to lead ourselves down a dangerous rabbit hole. So having sets be elements of other sets is fine. Having sets being an element of itself is what caused things to go haywire. The axiom of regularity exactly prevents this issue, but actually a little bit more than just that. So for example, the axiom of regularity does not just prohibit a set being an element of itself. You could invoke as an axiom, there is no set A so that A is an element of itself. But the axiom of regularity actually prohibits a little bit more. You can't have like chains of containment, like A is an element of B and B is an element of A. These two statements together don't expressly tell you that A is an element of A. Notice these are not subsets, so I can't use transitivity. Okay, these are just elements. There's no reason why, without the axiom of regularity, that is, that you couldn't have A is an element of B and B is an element of A. The axiom of regularity does actually prohibit this. Or a three-step process where A is an element of B, B is an element of C, and C is an element of A, and so on. Okay, so the axiom of regularity does not only prevent sets from being elements of themselves, it prevents sort of chains from closing up on themselves like this. Okay, we're not really trying to do an incredibly detailed look into axiomatic set theory, so we're not going to talk about this all that much more. The point here is just, Russell's paradox showed that intuitively assuming, oh, let's just talk about the set of all sets, led us to some very bad places. Okay, so relying purely on intuition for definitions can be very dangerous. Just because something seems reasonable enough, oh, the set of all sets. Sure, I can say it, so it must exist. No, the set of all sets is a contradictory object and cannot possibly exist. It destroyed our logical system to assume it was there. So you can't rely too much on intuition in mathematics. It's handy as long as you remember that everything has to be backed up with axioms and logical derivations. Relying too much on your intuition can lead you down some bad places and cause you to make mistakes.